Hi everyone. Good afternoon to everyone. This is Mohan Raj. Currently, I'm working as a data scientist in HCL Technology Chennai. You can reach me mentioned Twitter ID. So the main objective of this webinar will be different CNN architectures for object detection and classification and segmentations. So if you have any queries, I'll be spending the last 10 minutes for the QA section. So whatever questions you have, you can post it in the chat window. So I'll take it for the last 10 minutes. So this is the agenda about my talk or webinar today. So what is the need for deep learning, and so what is image classification and various CNN architectures for image classification. So and what is the object detection, and same things, various CNN architectures and technique for object detection. And finally, I'll be concluding with the image segmentation technique. And I have two demo. One is facial expression recognition using CNN architectures, and the other one which is a segnet pixel level semantic segmentation for roads in understanding. So these two demos I'll be running on the Google Colab, which is an GPU Jupyter Notebook access. So let me talk about, so what is the need for deep learning. So what is the difference between the traditional pattern recognition approaches and the current deep learning approaches. So for example, when you take any image sample, so initially we'll go for like handcrafted features like HOG or LBV or any mathematical features, statistical or histogram or textures or maybe key point descriptors. So it will be an application dependent. So I cannot reuse the same features for the other applications, and we'll use any machine learning classifier. So whatever features we extract and given to the machine learning classifier for the model training. So once we get we can make the predictions on the trained model. So, but the main thing is that so I cannot reuse the same features for the other applications. So, and it is an tedious and it is an complex features for the other applications. So let me go for the what is the deep learning. So in deep learning, we are trying to extract the features in the hierarchical levels from the low level to the high level features. So when I reach at the high level features, those features are more discriminant between the other objects. And in case of deep learning, it is an end-to-end model training. So we'll give you input images. So finally, we'll get an results. So you could see the features, intermediate features between the low level and the high level features. So we'll be having several various CNN architectures for the in case of classification and detection and segmentations. So let me first start with the image classification. So I just want to give you what is image classification. So in case of here, you could see there is a dog on the right hand side. So in classifications, we are trying to assign a label for the whole image, whatever I feed it to the CNN architectures. Finally, the systems or model will give you the probability scores. So in this case, I have totally 3 classes in my model, which is trained. So which are dog and cat and pandas. So finally, the models give you the probability for those 3 classes. In this case, dogs are 95% and cat is 4% and pandas is 1%. So out of these 3 probability score, we have the dog which has the high probability scores. So that will be given as a machine predicted. So initially what we do, we'll give you a set of samples for the whole classes. In this case, a cat and dog and pandas. So we are giving several samples for those classes which machine want to predict on the test time. So based on that model training, so now the machine has the capability of what is cat and what is dog and pandas. So based on that, finally we are getting the probability scores for the whatever the image which we are giving it to the model. So let me go more detail about so in this case we are going to discuss about so what is the semantic gap. So how we perceive images as a human being and how we represent the image to the machines. So you could see in the right hand side we have 2 samples, which is a cat and dog. So those are in case here all the images are represented as a 2D matrix. So each matrix will have n number of rows and n number of columns. So we are representing the images in a pixel. Right. So in this case, we have a cat matrix and the dog matrix. So we are representing the image as a matrix to the machine. So, is that possible to do a classifications by the machine by looking at this pixel value? These pixels values are between the 0 to 255. So either it may be dark or it may be a white, or we'll have a gray shades between the 0 to 255. right? So with this pixel value, the machine cannot distinguish between the cat and dog, because when I look at as a human being, when I look at any image sample, first I'll go and look at what is the characteristics of the object. For example, if I want to represent the apple, so I'll look at the color and the texture and the shape, right? So based on the human characteristic, the object which we are looking at, so based on that, the human is classifying what kind of object it is, right? So but when in case of machine, we are representing as a 2D matrix. So how our machine will capable of classifying those objects? So that is the reason there is a gap between how we perceive images and the machine representation. So to fill this gap, we are going for the feature extraction technique. Like either we may extract the spatial features, or maybe a color, or maybe a texture, or maybe a combinations of hybrid features. So here the feature extraction, we are going to extract some numerical value out of the whole matrix. So that represents what kind of object it is. So those features we are giving it to the machines for the classification, instead of giving the raw pixel intensity value, which are we'll call it as maybe a grayscale value or maybe a pixel intensity value. So the features are most important when the machine wants to do a classifications. So what are the challenges when you want to do any image classifications? There may be several challenges. So I'll be listing few of them here. So you could see on the left hand side we have several challenges. So you could see the first one, which we'll call it as an orientation at the angle. So you could see there is a board which we'll call it as a Raspberry Pi board. So the same image which was taken on the different angle and the orientations. So how you can do a classification? Even the image is taken on the different angle or different orientation, how your feature extraction algorithm will be robust enough to do a classifications. So though I'll take the zero angle, or maybe side angle, or maybe a left side, or it may be right side, or top mounted camera, or it may be a frontal faced camera. So though if I take images on the different angle and the orientation, the algorithm or the model should do a classification properly. So this is the one first challenges. So going back to the second one, so the next one you can see the images which has the proper lighting condition, and the other one which you have the darker lighting conditions. So how the images get formed when you are trying to capture any images, two components are important. So the amount of illumination which is reflected back onto the object. So we will call it as an I into R. So here when you want to form any images, the illumination component is the most important. So if you are taking the outside or outdoor environment, the images looks more brighter because you will have the sunlight. If you are trying to take the same thing on the night scenario, the most of the pixel values will be closer to zero because there is no lighting informations, right? So the most important thing when you want to do any image classification, you could see like there is a proper lighting conditions which the image was taken. So these are the few challenges you need to be considered. So coming back to the other one, which we'll call it the scaling, right? So in this case, scaling in the sense when the camera is closer to the object, or when the person is when the object is far away from the camera, so the object looks smaller, right? So in this case, you can see there is a coffee cup which was taken in the different distance between the camera and the object. For example, if I'm closer to the object is closer to the camera, the object looks bigger, right? So if the object is far away from the camera, then the object looks smaller. Though it was taken in the different scale, the machine learning or the deep learning algorithm has to do a classifications properly. Right. So coming back to the last one, which we'll call it an occlusions, right? So you could see the same dog images, which is there on the left hand side as well as the right hand side, two columns. So on the left hand side, we have the proper visual images, which is clearly visible. We can the machine can do a classification saying that it's a dog. On the right hand side, the same images which is occluded, the object is occluded with the some other objects, right? Maybe some, in this case there is a towel which is occluded on the dog. So only we have the few visual features of the dog. So how we can do a classification even the partial of the object is occluded. So these are some of the challenges when you want to build any image classifications algorithm, maybe a machine learning or maybe computer vision or maybe deep learning approaches. We have to see to that our algorithm or the deep learning model is capable of overcoming these challenges. So coming back to what are the different CNN architectures. So I have taken till 2015. So till ResNet I have considered here. So which I'm starting from the VGG 16 and then 19 and then Overfit and then GoogleNet. and residual network. So let me give you some outline about these 5 architectures. So in case of VGG16, there is a 13 convolutions layer and then 3 fully connected layers. So finally, the VGG16 architecture is capable of doing a classifications of 1,000 classes. So this was actually for the ImageNet data competitions, which occurs every year. So you can also participate on that competitions where you can design your own deep learning architectures which can perform better than the existing one. So coming back to one VGG19, so which has the 16 convolutions layer and 3 fully connected layer. So the same thing, it also does the 1,000 image class labels classifications of the 1,000 classes. And coming back to one overfit, where we have 5 convolution layer and 3 fully connected layers. So totally we have the depth of the layer, which we'll call it as a 8. In this case, VG16, we have 16 layers. So that is the reason 16 VGG16. And 19, we have 19 layer, 13 convolution plus 3 fully connected layer. So coming back to one GoogleNet. So what is the difference between the VGG16 and 19 and the overfit? So in case of here, in GoogleNet, we have deeper convolutions. So in earlier case, you would have seen in each layer only one convolution. But in case of GoogleNet, we have within the convolution, we have several parallel convolutions we are trying to do with 1 cross 1 convolution and 3 cross 3 and 5 cross 5 convolution. So we are going the deeper level of feature extraction, where we will get the more robust features when compared to the like VGG or overfit. So we have several overfit inception layer in the GoogleNet architectures. So you may look at this architecture in the offline. Maybe you can search it Google Inception V3 architectures. So coming back to one residual network. So here the residual networks are most important, because when in deep learning, what we are trying to do, we are trying to keep on increase the the depth of the layer, right? So we are going till 100 or 150 or maybe 200 or maybe thousands, right? So when you are increasing the depth of the layer, so the loss or the accuracy should increase, right? The loss should decrease and accuracy should improve, right? So, but the actual plain network, what happens after some layer, there may be a degradations or there may be increase in the loss. So the residual network, even if I increase the number of layer, the loss won't increase. The loss will keep on decrease, or maybe it will be the stable positions. So that is a residual network. People will call it as a skipping connections. So maybe you can go through the offline architecture. So out of all these, the residual network architectures performs better. So which has the lesser loss functions, loss values. So coming back to one LeanNet, so this was designed specifically for handwritten digit recognitions. So maybe you would have came across the data set called MNIST. So this was purposefully designed for the recognition of handwritten digit recognition, which are between the 0 to 9. So whatever the input data which I pass on to the LeanNet architectures, finally it will give you the 10 probability scores. So where it gives the classifications for the whether it's a 0 character or 1, or it may be 2, or it may be. So we'll have totally 10 probability scores. So out of that, the maximum probability scores will be chosen, and that class label will be assigned. So that's what all about image classifications. So now I'm going to talk about, so what is the object detections? Okay, so till now we have talked about image classification. So we are trying to assign a class label value. So I'll give you some input data to the machines or the model. So finally, the machine will give you the probability scores. For example, I want to do a classifications of cat or dog, right? So I'll get 2 probability scores. Based on that probability score, finally, we are trying to get which has the maximum probability, and we'll say that is the predicted classes, right? But the machine will not give you which region my target object is present, right? But in this case, you could see there's a cat. So the machine is giving a dog or cat, whatever it may be. So in this case, we have a dog as a machine predictor, but the machine does not have the knowledge where exactly the cat is present, right? For example, when you have a multiple objects are present within a single image, right? So those cases, we should get the region as well as the class label. So that's what here in object detection. So in object detections, we are going to do a classification plus localizations. So first, so both combinations of classification and localizations, we'll call it an object detection. So that's what we are going to discuss more detail about object detection. So this is the various, from the 2006 to 2016, what are the object detections mechanism. So till 2012, it was an handgrafted features, which we'll call it in computer vision based technique was used. You could see the accuracy level. It was close to around 40% for the object detections. When the deep learning concepts was started, so you could see the accuracy it keep on increasing. It was reached almost the 80, close to 80%, right? So maybe there are several CNN architectures are there for the object detection. So in the subsequent, I'll be discussing about that. So before going into an object detection, I just want to give you what is a sliding window, right? So you could see the animations here. In sliding window, what happened? There will be images will be there. So we have created a constant, window, so which we are sliding from the left to right till we reach the last pixels in the images, right? So in earlier case of in image classifications, what we did, we have taken the full image and we have extracted the features, and then we have done the classifications and we got the probability scores, right? But in case of object detections, I cannot take the whole image. Instead of that, so I'll create some patches of sub images. So for each sub images, I'll extract a features and then I'll give it to the machines for the classifications, whether those regions my target objects are there or not. So the similar way, so I'll get multiple sub images for the single one, and finally I'll get the overall results. So then we'll get the where exactly the target object is there. So that's what which talks about the sliding window. So here, for example, in this case, I have one sliding window which I'm passing to the CNN architectures. So which here the reference architectures was the AlexNet. So finally, it goes to the classification saying that whether it's a cat or whether it's a dog or whether it's a background. So the similar way, we'll have the several sub-region, each sub-images which pass on to the CNN architectures. So finally, the machine gives you the probability scores, whether it's a cat or dog or background. So based on that, we'll get a multiple results for the single one. So finally, we'll apply a NMS technique, which is a non-Maxima subtraction technique, to make a final bounding box. And then we'll also, some of the classes also will make the, based on the probability scores, we'll keep a threshold. Whether it's below certain scores, then we are going to eliminate those are not objects. So here, so if you are applying a sliding window kind of concept, there may be several sub images. There may be a possibility of 1,000 or 10,000 or lakhs of sliding window or possibles, right? So to avoid that, so there is a concept called the selective search algorithm. It uses the simple textures or color features where it gives you there may be a possibility of object. So only I'm going to apply the CNN. I'm going to give only those regions for the feature extraction or maybe a CNN model for the object classifications. So in the case of sliding window, we'll get a multiple regions. So to avoid the time computations, maybe people are started using selective search algorithm where there may be possibility of target object. So only we are going to apply the pass these regions to the CNN to make the object classifications. So there are so before deep learning technique, there are techniques called histogram of oriented gradient and linear support vector machines and Haar cascade. So I just want to go through what is histogram of oriented gradient. So which has the 5 steps. So people use a pre-processing technique, which we'll call it as a normalization, and compute the gradient in x and y direction. Obtain the weighting out of cells for the each cells, and then concatenate all the cells into block, and finally concatenate all the blocks into a single HOG features. So this is the gradient computations for the x, and the second one, which is the middle one, gradient computations for the y. So we are going to compute the g, which is a single gradient magnitude value. So which square root of gx square and gy square. We'll have an input image, which is called it as a I, and we'll have a x direction kernel, which is a dx. And in this case, we have used a Sobel kernel. So do a convolutions along with the input image and the x direction Sobel kernel. So we'll get the gx results. And similarly, we'll get the gy results. So finally, to make the gradient magnitude value, so we are taking the square root of gx square and gy square, so which is a gradient magnitude, and the orientations will be calculated, which is called the theta, the tan inverse of gy divided by gx. So for each pixels, we are trying to compute the gradient magnitude and the orientations. So once we calculated the gradient magnitude and orientations, so we are trying to divide the gradient magnitude images into cells. So there may be a less number of cells or more number of cells. So here you could see for each cells we have less number of pixels, but in this case we have within the cells we have more number of pixels. So we need to decide what is the number of pixels for each cells. So based on that we will get the number of cells. So once we get the splitting of into cells, we need to calculate the gradient magnitude oriented histogram. So the x direction will be the orientation and the y direction is the magnitude. So once I got the gradient magnitude and the histogram for each cells, then I'm going to form a block. So in this case, I have within the block I have 4 cells, which we will call it the 2 cross 2. So now I'm from the cells I'm forming into a block formation. So between the each block to the other block, there is a 50% overlapping between the each block. So now I formed a block. From the block, finally what I'm going to do, I'm going to concatenate all the blocks into a histogram of features. So the main speciality of HOG will be the it will give you the structural shape, which is the discriminative structural shape of the object. So I have given the myself images, and finally I get the structural shape where the head, you could see the head and the hand and the remaining portions. So the main HOG was used for the human detections kind of objects. So this was especially used for the object face detection and the human detection, and even people are customizedly they are trying to use. So coming back to the other one, which I call it as a Haar cascade. So this was in 2004 until 2006. This was the most famous technique, which we'll call it as an Biologons based face detection algorithm people were trying to use. So many of them may be real timely, they may be tried out using OpenCV based face detection, which is readily pre-trained models are available for the face detection. But there are some drawbacks when we use an Haar cascade based face detection. There may be a more number of false positive face detections rate. There are some region may not be in phase, but the algorithm will give you as a phase. But the main advantage of Haar cascade will be it is faster in real time. So it can perform the real time based phase detections algorithm. So now I have discussed about the computer vision based technique before 2012. So now I'm coming back to one which is an deep learning based technique. The first one which is an region based convolutional network, which is an RCNN. Maybe many of them familiar with that. So here the RCNN also uses the selective search algorithm to get the which are the region possibly the the objects. So only those sub images we are going to apply the CNN for the model classifications. So first we apply the selective search algorithm and get the which are the regions are possibly object, pass those patches or sub images to the CNN. Finally we'll get the probability scores are the for the each classes, and finally we'll get the bounding box for the target objects. So let me go back to the visual architecture explanation for the RCNN. So here you could see on the left hand side we have the input images, and by applying the selective search algorithm I got the certain number of number of the region which are possibly the object. So only those regions I'm going to apply the CNN model. So get the first ROI or the first sub images and pass that images to the CNN. Finally do the classifications whether it is a person or whether it may be XX or object. So similar way, we are trying to apply the for the other sub images sequentially. It will be applied for the remaining sub images also. Finally, we'll get the results of overall bounding box results. The same thing here. It is also given. So for each sub images, or there may be possibility of object. We are trying to apply the separate connet for the classifications. The main drawbacks of this RCNN are time consuming, because we are trying to apply for single image itself. We are trying to apply the CNN for the multiple times, right? For each sub images we are cropping out and passing onto the CNN for the feature extraction and classifications. So there may be multiple regions or multiple maybe 1,000 or maybe 2000 of object may be possible. So we are trying to pass those regions to the CNN, right? So it will take more time. It may not be feasible for the real-time object detection. So there is another technique which are proposed, the next one. So that I'll talk about a little bit later. So before that, I just want to say a few things about what is image pyramid. Okay, so on the bottom you could see there are two images on the left hand side and the right hand side. So we have both the images which are represented in the green color, the dog one. So in the left hand side we could see the smaller scale in the dog, and the right hand side we have the larger scale in the object, which is a dog, right? So when you want to do any object detections algorithm, we should create the a pyramid kind of stuff for the multiple scales of images we have to construct, and apply the object detections on the each scale of the images, and finally use the NMS technique, maybe because we are trying to apply the object detections on the multiple scale, so we'll get multiple bounding box for the same images. So this is the reason. So why do you want to apply the image pyramid? So to represent each image in the multi-scale representation and apply the object detections on all the scale of the images. So we'll try to get the proper results. Though even if the objects are smaller in the scale, if we apply image pyramid technique, it will not miss out the objects. So here, so when you want to build your own object detections algorithm, so what are the steps needs to be followed? Okay, so the first one, we have to apply the sliding window technique, or maybe a selective search algorithm on the each scale. So you could see maybe you can consider 500 cross 500. The next scale will be a 250 cross 250 and 120. So we can keep the minimum scale. So till that we'll construct a pyramid and apply the object detections on the each scale of the images and extract the features and use any linear SVM or maybe a deep learning technique. Finally, use the NMS technique to combine the results. So maybe I'll talk about more detail about what is the NMS, which is a non-Maxima subtraction. So we are trying to apply the object detections on the image pyramid, which is a multiple scale of the images, and each scale of the images will give you one bounding box, right? So on the left hand side, you could see after applying the image detection or object detections on the multiple scale, for single car we got multiple bounding box, right? So but there is only one car at the input image, but we got the several bounding box. So because of we applied the object detections on the multiple scales. So to avoid this kind of overlapping bounding box, so we are applying a non-Maxima subtraction. So it works basically the ratio of the amount of overlapping. So which has the more overlapping, the bounding box. So that will be the final predicted results. So you could see the green color bounding box, which has the more overlapping. As I said, there is an RCNN, which is a region-based convolutional neural network. I was mentioned about it is a time consuming. So because we are trying to apply the CNN model for the each sub-regions or the ROI, right? So the other author, which they have proposed, which is a faster RCNN or fast RCNN. So instead of applying the CNN for the each patch images, they are trying to get the input image, apply the CNN architecture, and get the feature map. From those feature map, get the possibility of region which are object. So only do a classifications for those regions. So in earlier case, what we did, first we applied a selective search, get those are the region, which are the regions are possibly object, and crop those region, apply to CNN. So we have applied the CNN several times, so that gives the more time consuming, right? So to avoid those problems, what people are done, so instead of applying for the each patch images, we are trying to apply the CNN model for the overall images and get the feature map. From the feature map, find out which are the regions are possibly object, only do those classifications. So it reduces the, there is a possibility of real-time based object detections. So that's what the improvement between the other one. So coming back to one SSD, which people are called as a single shot detector. So the SSD basically works on top of the VGG16 architectures. So they removed the fully connected layer, which are three fully connected layer. So so here you could see on the input image, which goes to a VGG16, and we are considering till the convolution 5 layer. From those feature map, we are trying to do a object detection. So here we are trying to do object detections on the multiple scales. For example, I got the feature map, which is the 200 cross 200 from the VGG16s, right? So I'll give it to the object detection. Again, I'll reduce the scale and give the object detection. So you could see on the here 19 cross 19 and maybe 10 cross 10 and again 5 cross 5 and 3 cross 3, and so we are trying to do the object detections on the multiple scales, and finally we are trying to apply the NMS. Like what we did on the similar way image primate, so we got the feature map. From the feature map, reduce the scale of the feature map every time divided by 2 and apply to the each feature map after dividing into by 2, give it to the object detection. So finally we'll get the several results, apply to the those bounding box results to NMS to get the final results. So coming back to the other one, which is an yellow network, you only look once. So it basically works by dividing images into grids, and for each grid we are trying to get the n predicted score or probability scores. So based on that score, threshold value, if it is above 30% of confidence score or the probability scores, so we are going to consider as it is a predicted class as a true, or else we are going to eliminate those regions are not the particular classes. So you could see the example here. So this is an input image which we have divided into 8 cross 8 or maybe a 5 cross 5 grid. For each grid, it gives the probability scores, maybe based on the classes. Here it is color coded. So based on that, finally we are trying to make the predictions for that. So this is all about different CNN architectures for the object detection. As per my knowledge, there are several other architectures also there. Maybe you can look at. So coming back to an image segmentation. So this was actually on the perspective of roads in understanding, right? So nowadays everyone are talking about autonomous cars, right? So how does the car is capable of understanding the road scenario? So there may be a auto vehicle is moving on the road scenario. There may be a vehicle which is moving on behind the car, and there may be a person may be crossing. There may be a traffic sign, or there may be a building, or there may be a tree, right? This is understanding of road scenario. So for the in earlier case between the image classification and segmentation, we have for the classification we have taken the whole image. For those whole image we have given the class label, right? But in case of segmentation, this is the pixel level in semantic segmentation. So for each pixel, I have to do a classification whether this pixels is a road, or this pixel is a vehicle, or this pixels is a sidewalk, or this is a lane, or it is a tree. So here we are trying to do a classifications for a pixel level. So based on the probability score for each classes, we have a predefined color value for each classes, and based on that we are trying to give a color value. In this case, yellow or blue or whatever. So whatever predefined color value for the particular classes we are trying to assign. So there is an architecture called, which is this is the most famous used architecture, Segnet. So this was Cambridge University. So they have their own data set, Cambridge video data set for the roads in understanding. They have built it for this one for the 11 classes. So where they have a sidewalk, trees and building, and then persons, and then so similar way there are fence, and there are several things are there. Actually, when you comes to an segmentation kind of architecture, you could see there is an encoder and decoder. So what happened at the encoder, right? So in encoder we have a set of convolution layer followed by a pooling layer, right? So when you do one convolution as well as the pooling, the dimensions of the feature map keep on reducing, right? When you go a deeper layer, the dimensions of the feature map keep on getting reduced. But when you want to build a image segmentation, the output feature map should have the same dimension as your input image, right? So we have extracted the discriminant features in case of encoder, but in decoder we are trying to reconstruct the original dimensions. So that's what the reason people use an upsampling and then followed by a deconvolutions. So finally, so at the last layer we'll have the 12 as a depth and image dimension as a width and height, finally the depth, because for each pixel we'll get a 12 probability score. So we'll have the depth as a 12. So based on that probability scores for each pixel, finally we'll make a predictions. So that's what I planned for the technical explanations. I have few demos I just want to walk through with that. So the first one, let me explain you the facial expression. So this was actually Kaggle dataset. So if you want to try these things, you can get the Kaggle dataset, which is an open source. Anybody can get the data. So actually I was using this Google Colab, which is having the Jupyter notebook access, where you can use the GPU based machines on the remote. So the only the thing is your code either should be in the the data and the input required files. Either you should move your data to a Google Drive, or maybe your data should be available on the GitHub. So in my case, my data, everything I have moved into my GitHub repository. So I'm trying to run the cell by cell. So I have several cells. So let me run these cells one by one. So first I'm trying to import the necessary packages. So here I'm using Keras and backend as a TensorFlow. So for creating the layers and the model training and then predictions. So now I'm trying to get the Kaggle data, which is available on the my GitHub. So once I get the data from my GitHub, then I'm trying to it was there in the tar file, so I'm trying to extract my tar file. So once I extracted my tar file, so I'm trying to visualize the few data from my the whole. So it was there in the CSV file. You could see there is a 3 column. The first column which says that what is the emotions. So totally we have 7 emotion which are between 0 to 6, and the second column which represent the pixel value. So totally we have 48 cross 48. So those are flattened into an 1D vector, and the third one whether this data for the training or the testing. Okay, so now I'm trying to split the data into the training and the testing. So first I'm trying to extract the training data. So once I extract the training data, then I'm trying to apply the one-hot encoding for the label, because we have to convert the numerical data into binary representations. So totally I have 28,709 data for the training, and number of pixels value, it is at 2304. So now I'm performing an one-hot encoding for only the class label. Then I'm trying to reshape the whole data. So because you have into 1D, so that 1D data I'm converting into a 2D data. So now out of the whole sample, I just want to visualize the few sample on the data which I read. So I'm trying to visualize the 12 data, which is a 3 rows and 4 columns. So now I'm creating the CNN architectures. So here I have around convolution followed by a batch normalization, and several convolution again batch normalization. Finally, I'll have the output layer, which is a 7, because I have 7 different type of facial expression I want to do. So totally I'll get 7 probability scores. And the input data here I have 48 cross 48. And then so here I am using a loss function as a categorical cross entropy, because I'm using a multi-class. And weight optimization mechanism I'm using Adam. So finally I want to get the metrics in the accuracy. So now if I give model.summary, so what will be the output shape for the each layers? So I have several convolution and the max pooling. So I have given 48 cross 48 as a input data, and 64 different filters. So I have used a 3 cross 3 kernel with a style of 1. So without zero padding, if we apply, so you will get the feature dimension, which is reduced from 48 to, we are reducing into 46 cross 42. There are 64 different filters, so the depth will be 64. Similar way, we are trying to perform several convolution and then max pooling. So finally, we'll get the 7 probability scores on the output layer. So now I'm trying to start the model training. So once I so the model training is over, so I'm trying to store the model weights on the h/5 file. So so I have given 10 epochs. I'm just skipping this thing. So already I have the trained results. So I'm trying to plot the what is the training accuracy and the validation accuracy. So this was the for the loss on the left hand side, and for the right hand side we have the accuracy. And then so I have taken only the training data to make the test data, to make the predictions and the evaluation on the test data. So I'm trying to read the test data. So once I have the test data, so this was the predictions results. So both are, if it is a green, then it is a ground truth as well as the machine prediction, both are equal. So if it is a ground truth and machine predicts are different one, then it is represented as a red color. So this accuracy was around 50% because we have not used any complex architectures. So maybe you can try with some complex architectures and you can increase the number of layers or maybe a number of filters. There are several hyper parameters are there to tune the CNN architectures to make the better performance. So I have one more demo which I want to showcase. I think I have talked about pixel level semantic segmentation, which is a Segnet. So for these things, I'm using the GitHub repository from the Segnet paper. Similar way, I'm trying to import the necessary libraries here. So once you imported the necessary libraries, and some cases there are packages may be missed out, so you need to install the few packages on the Google Colab. So to install the library, you need to use pib install. The same thing, only these special characters you need to add before the pib. So I have imported the necessary libraries, and then I'm trying to normalize the pixel values of those image data which are between 0 to 1. So once we are normalizing the data, then we are going to create a deep learning architectures for the encoder and decoder network. So here this is a encoder network, the first portion, and the second portion is the decoder network. So here I have taken 360 into 480 is the input data. So and we have a color images which we'll call it as a number of channel will be the 3 into 360 into 480 as my input data. So once you are done, then we are trying to add the loss function and then optimization and the metrics. So then we are trying to give the model.summary, which gives the what is the output of the each layer. Then finally we are trying to start the model training. So here I have given 10 epochs. Maybe you can increase the number of epochs. So when I gave number of epochs as a 10, so I got the accuracy around 63. So when I gave epochs as a 100, the accuracy was around 83%. So this is also one parameter where you can get the better accuracy. So once I done with the training, the model weight is stored on this particular name. So I'm trying to load the model weight to make the predictions. As I mentioned, for each classes, we have given the predefined color value, and the 12th one, which we are calling as unknown classes, which will be represented as a black color. So finally, we are trying to make a prediction. So this is the input image, and finally, we are getting the results. So maybe this actually people are using for the many use cases. Like for the medical images, also people are trying to segment the regions, left ventricle and the right ventricle. There are several applications also you can use, for the say pixel level semantic segmentations. So that's all about my presentations. So now I'm moving forward for the QA sections. So I'll be stop sharing my screens. So to answer for the custom object detections, right? So whenever you want to do any object detection, you need to have the annotation files. So the annotations in the sense, we have to have the bounding box regions, which are to answer for the custom object detections, right? So whenever you detect, you need to have the annotation file. So you get the annotation file. So once you have the annotations file, though based on that, the objects features are extracted for the training. So in the cases alone, we'll try to apply this sliding window, and each sliding window features based on the already trained model features. We'll try to match whether the target object is present or not. So you can create the you can generate the training data and select the which are the regions on the training data your target object is present. So you need to have the, and then you create the trained model and make a predictions. Maybe I can share you some of the TensorFlow object detections APIs are there where you can build on top the CNN based model for the object detections. So I'll go for the next question. So I'll be sharing the link and my Twitter ID. So maybe you can reach me in the offline if any details regarding object detection and classification and segmentation. And you can search on Mohanraj MIT. So the GitHub link where I uploaded those IPython notebook file. Directly you can open those IPython notebook from the colab. You can run each cells, and then you can visualize the model training results. So the useful related resources for the particularly for object detection using deep learning. So those resources links also I'll share where you can try for your own custom object detection and classification, and similarly for the segmentations. Thanks everyone for attending this session. Thanks for the School of AI for giving me this opportunity.